This video is about directional derivatives. Okay, first of all, let's see what is directional derivative. Okay. Think about it, we have a surface, okay, a function fxy is equal to fxy. We know its graph is a surface. X, y, and z. Think about a point. Say x naught, y naught, and this point to go up will be a point on the surface. Okay. Now, before we talk about the directional derivative, let's recall what is the partial f respect to x. Okay. So remember, we treat y as a constant. Okay. Here is y, y0. Okay. Now, let y equal to y0, which is a plane. Go up, intersect your surface, you will get a curve. Okay. Then partial f respect to x give you slope of tangent for that curve. Okay. Then similarly, you can fix x at x naught. In other words, let x equal to x naught. Then you go up, intersect your surface. X equal to x naught is a plane. Okay, this plane parallel with yz plane. Go up, intercept your surface. You got another curve. Okay. Then partial f respect to y give you slope of tangent for that curve. Okay. So basically, we just say find the derivative along this direction, and the y is the final derivative along the other direction. Basically along x and y. Okay. How about we just go with any direction u? Okay. U there equals is a vector on the xy plane. So you can write a and b. Okay. So if we go this way, then think about I have a plane. Go up. Just like what we did before, intercept your surface, you got another curve. Okay. How about I want to find the slope of tangent for that curve? That is what we call the directional derivative. Okay. And this u can be in any direction. Okay. Can be here or there, so on and so forth. Okay. Okay. Directional derivative. We use on the direction u, we use duf to define. Okay. Evaluate x naught, y naught. The definition for that is a limit h go to 0, f x naught plus a times h. A this a, okay, and y naught plus b times h. Then minus fx naught y naught over h. Okay. X naught plus ah, y naught plus bh. This point will be on this line. Okay, I'm not going to prove that. In fact, this one can be found. In fact, it can be proved. To find the directional derivative along direction u at a point x and y can be found by this formula. Partial f respect to x at xy times a plus partial f respect to y fxy b. Okay. Here u here equal to ab is a given direction x and y. U here is a given direction. Okay, very important here. U here must be unit vector. Okay. In other words, if you want to use this formula to find directional derivative, you have to make sure that U here is a unit vector. Otherwise, your answer will be wrong. Okay. Now we have if we define gradient f like is a vector, okay, fx, fy, okay, then the directional derivative have a short way to write that is a gradient f dot u. Okay. If you forget about dot product, go back review. Okay. Which is fx, fy inner product a and b. Okay. Okay. Now, obviously, for the given u, whenever you give me a direction, then you can corresponding to a curve on the surface. For the different direction, you got a different curve on the surface. Its slope of a tangent will be different. Okay. Now we have the question for which direction u directional derivative reaches the maximum. Okay. Okay. Now, since directional derivative is equal to gradient f dot u, and try to recall two vector dot product have a formula. It's like gradient f, it's a magnitude times gradient magnitude of u, then cosine theta. Okay. Now, this is like this. U is a vector and the gradient f is another vector. Theta here is an angle between those two variables, two vectors. Okay, for given surface, f has been given, so this vector has been given. Now, when you change the u, then you change the directional derivative. Okay, obviously, okay, and this one is equal to magnitude of f. Remember, u is a unit vector, therefore this one is 1, so you go cosine theta. Okay. So when you change u, that means you change the theta. Okay. Obviously, when theta equals 0, this reaches maximum. Okay. So the maximum of directional derivative for all the u is equal to magnitude of f. Okay, its maximum can be reached when theta is 0. What that means? That means if you take your u same direction, of gradient f, then your maximum has been reached for directional derivative. Okay. Okay, now let's look at an example. Okay, example. We have given fxy here is equal to x e to the y. Okay. Now we want to find the rate of change. Find the rate of change at a point p to 0. Okay. In the direction from P to Q, from P to q. Q is another point, which coordinate is 1/2, 2. Okay, so we want to, this is question A, okay? We want to find the rate of change, in other words, directional derivative, at a point P in the direction to PQ, okay? And the part B, we want to, in what direction? Well, second, we want to find the maximum of directional derivative, okay? And also, in which direction the maximum has been reached. Okay, first of all, let's find the rate of change for this function at p in the direction of from p to q. Okay. In other words, we want to find the directional derivative at a point 2, 0. Okay. The formula for that is a gradient f evaluated 2 and 0 and times u. Okay. Remember, u here have to be unit vector. That's very important, okay? So, in order to find a directional derivative, we need to find two things. First of all, we need to find this, 2, 0, okay? Find the gradient. To find the gradient f, evaluate 2 and 0, first of all, we have to find what is the gradient f. Okay. Gradient f there is partial f respect to x, partial f respect to y. Okay. Now let's first of all find the partial f respect to x. Okay, go back to here. Partial f respect to x, you treat y as a constant. So e to the y is a constant. So partial f respect to x give you e to the y. Okay. Then partial f respect to y, you treat x as a constant. Then you take the derivative of e to the y, it still give you e to the y. Okay. Okay, then we find the gradient f, then we have to find the gradient f, evaluate at 2 and 0. Okay. What that means? That means whenever you see x replaced by 2, you see y replaced by 0. So the first one, e to the 0, give you 1. Okay. The second one is 2 times, x is 2, times e to 0, which is 1. So that's it. Okay, okay, now let's find u. Okay. They said u is in direction from P to Q. Okay. P to Q is use the point of Q, subtract coordinates of P. Okay. So should it be 1/2, 2, subtract 2 and 0. Therefore, my PQ, this vector is negative 3/2, then 2. Okay. So the question is this our u? No, we know u in its direction, but this one is not a unit vector. Therefore, my u should be vector PQ in that direction, but divided by its magnitude. Okay. This divided by this scalar will not change the direction, only changes the magnitude. Okay. So what is the magnitude of PQ? This vector. The square roots negative 3/2 square plus 2 square. You simplify that, give you 5/2. Okay. So u there is equal to 1/5/2 times PQ. PQ is a minus 3/2 and a 2, and this give you minus 3/5 and a 4/5. Okay, now we're ready to find its directional derivative. Directional derivative of f. Evaluate at a point 2, 0 in the direction from P to Q, which is gradient f 2, 0 times u, okay, which is gradient f 2, 0 is 1 and 2, okay, and my u here is -3/5, 4/5, so equal to minus 3/5, 1 times -3/5 plus 2 times 4/5, so give you 8/5. So you got a 5/5, give you 1. Okay, so we finish part A. The rate of change of your function along direction from P to Q at a point 2, 0 is 1. Okay. Now the question B. Okay. What is the maximum rate of change? Remember we say that in general the maximum rate of change is, for all the u, is the magnitude of gradient f. You have maximum rate of change of 2 and 0, okay, which is the magnitude of this vector 1 and 2 is square root 1 square plus 2 square, square root of 5. Okay. So this square root of 5 gives you maximum rate of change. Okay. Remember, the maximum rate of change is happened in the direction you take the direction as a gradient f 2, 0, which is 1, 2. Okay. If you chose your u in the gradient f direction, which is 1, 2, then you reach your maximum rate of change. Okay, why you go to the, let me give you a little bit of explanation why you take a gradient f, then you reach your rate of change, achieve its maximum. Okay. Now, let's go back to this. Something to do with, say, level curve. Okay. We talked about level curve before. Okay. Now, this is the surface. Okay, I give you this function means I give you surface. What is a level curve? Level curve is this is surface and z equal to k. What is z equal to k? Another surface, which is a plane. Intersection of those two surfaces give you fxy equal to k, right? Replace z by k, you got this. This is the curve. Okay. Let me give you an example. If z equal to x squared plus y squared, okay. What is the graph of that? X, y, and z. Remember, this is a paraboloid. Okay, like this. Okay, what is the level surface? For example, so this is my fxy. Okay. fxy equal to k. fxy, which is x squared plus y squared equal to k. For example, k equal to 1. Okay. Which means let z equal to 1 to say here's z equal to 1. intersectional surface, you got what? You got a curve, right? So level curve, this is your k, okay, equal to 1. You got circle with 1 as radius. This is 1. Okay. If I let k equal to 4, then I got another, if fxy equal to 4, you got another curve, a level curve, okay, which is like that, equal to 4. So that means you let z equal to, say, 4 here. Z equal to 4 is a plane. Intersectional surface, you got another curve. This curve is another circle with radius what? Is 2, right? You take square. So the radius is 2. Okay. Okay. Now, fxy equal to k is a curve. And this curve also can be written like this. Remember, any curve can be written like this. xt, y of t. Same curve, okay? This circle also can be written this way, okay? So since they're talking about the same curve, you plug in here. Replace x by xt, y by yt, okay? They're talking about the same curve. Therefore, this equation should be satisfied. Okay. Now, use the chain rule. I take derivative with respect to t, okay, like this. The right hand side, you take derivative to a constant, give you 0. Left hand side give you partial f. Use chain rule, okay? Partial x dx dt plus partial f partial y dy dt. The right hand side is 0. Okay? And this one can be written as gradient f, the short way to write that, and r prime, okay, equal to 0. Okay? Remember, what is r prime? We learned that before. R prime give you, for example, we're talking about this point. R prime give you, this curve is R. R prime give you, okay, talking about this point. R prime give you the tangent, slope of a tangent. Okay. Now gradient f dot the tangent direction give you 0. That means what? Gradient f is a perpendicular to the tangent here. So in the other words, if you are on the level curve k equal to 1, you want to go to the k equal to 2, k equal to 4. If you go this way, your z would change from 1 to 4. Okay, your z from change 1 to 4. This will be shortest way. If you go this direction, which is gradient f, or you go the other direction, for example, from here, 1 here, you go there. It could take much longer for you to get one level curve to another way. So that's why the gradient f, if you along this direction, your rate of change the fastest. Similarly, we can talk about the level surface. This one, what's the graph of this? It's a surface. Think about this. If you are able to solve the z from this equation, you will get a z equal to fxy, right? And we know this is a surface. Okay? That's why we call this a surface. Okay? Now, think about this surface. It looks like this. Okay. For the given point, think about this. This is a curve on that surface. Any curve on the surface, any curve, recall, can be written in this form: xt, yt, and zt. Okay. So think about this curve. in this form and also on the surface. What do we mean this curve on the surface? That means they will satisfy this equation. Okay, so you plug in there xt, yt, and zt. They should give you k. Okay, so my left hand side is a function depending on t, and for different t you got a different point on this curve. Okay, so I can take df dt. Okay, I take derivative with respect to t on both sides of the equation. The right hand side you take a derivative on constant, give you 0. The left hand side use the chain rule. You got a partial f respect to x dx dt plus partial f respect to y dy dt plus partial f partial z dz dt will give you 0. Short way to write this is gradient f, capital F, dot r prime. Okay, right? This is r. R prime take a derivative. Okay, equal to 0. Okay, what is r prime? R prime give you direction of your tangent line. Okay, so this equation means what? Your gradient capital F perpendicular to the tangent direction of this curve. So how about this curve? Okay, I didn't say which curve is that, right? There can be any curve on the surface. So then the other curve, you got another tangent line. Okay, so basically this gradient capital F give you vector. This is a vector perpendicular to tangent direction on any curve on that surface. So obviously that gradient F can play the role as a normal direction for the tangent plane, right? Therefore, remember, to find the equation of the plane, we need to know what? N, which is A, B, C, right? For this case, is gradient F. Therefore, and we'll also need to know a point on the plane, say x naught, y naught, z naught. Then your tangent plane can be written as what? A times A is partial f respect to x at this point. That's your A times x minus x naught plus fy partial derivative with respect to y at this point, evaluated at this point. Then y minus y naught plus partial f with respect to z, evaluated at this point. Then z minus z naught equal to 0. That would give you equation of the tangent plane. Okay. You said you probably recall we talked about tangent plane before. You said this one is how can you get a different formulas? Before, remember, we have the, if I give you surface in this way, we find the equation of tangent plane. Now here we give you a surface in its implicit form. Then we'll have the other way to find tangent plane. In fact, if I give you function in this form, you really can be right like what? This one you can say fxy minus z equal to 0, right? So in this case, my fxyz equal to this special form. Therefore, my capital gradient f is partial f with respect to x, partial f with respect to y, partial f with respect to z. Okay, so what is partial f with respect to x? Look at it here. you take it partial derivative with respect to x, right? So give you fx. Then the second one, z is there's no okay. Why you take a partial derivative? You trade respect to x. You trade yz as a constant. So that's it. Okay. And the partial f respect to capital F respect to y. So you got a small fy. And the second one you take a derivative, give you 0. Then the partial f, capital F respect to z. The first one there's no z. Trade as a constant, give you 0. Then you got a -1. Let me write this. Partial f respect to x. What's your f? Your capital F is fxy minus z, right? You trade yz as a constant. So it's simple to give you this. Okay, then you just plug in there. So you got x naught y naught times x minus x naught plus capital Fy, which is capital Fy is small fy, x naught y naught times y minus y naught, then plus capital Fz, which is -1. So z minus z naught give you 0. So let's add z minus z0 on both sides. We got this. Plus fy x naught y naught y minus y naught. So this go back to what we had before for the equation for tangent plane. They're really same thing.